Just wait for that. They can ask him during the presentation. Yeah, yeah. You alert me when there is a virtual question. You can just wait for a pause at that time, just wait, and you can alert me to the virtual questions that are coming online. I'll take them. Acha, 20 seconds. Okay. Sudhir, you can start. Whenever I'm ready. You need this to with the online guys might not hear you. Without- It's okay. Let me use this for the moment. I'll take it. I hope I'm audible with the online audience, and I hope I'm audible here. So, is it working? Maybe. Maybe. Okay.
Hello. I hope it's audible now. So it's, I'm glad to be here at SPCon for the tutorial on SPCon on strategic communication. Welcome everyone to this talk and also to the online audience. So let me just introduce the speaker and I'll give like a brief description of the logistics of the session, and then we can get started with Professor Ankur Kulkarni talking on strategic communication. So this tutorial is on strategic communication, which is given by Professor Ankur Kulkarni. Professor Ankur Kulkarni is a professor, associate professor at IIT Bombay. So he presently serves on the IT Project Advisory Board of the SEBI, and also as a research advisor to TCS. So he received his BTech from IIT Bombay and did his masters and PhD from UIUC, University of Illinois at Urbana-Champaign. So he was an associate of the Indian Academy of Sciences, Bangalore, and he has been an editor for several conferences, recipient of the Inspire Faculty Award, and he has uh, multiple Best Paper Awards and Excellence of Teaching Award in IT. So he has been MIT in USA, University of Cambridge in UK, NUS in Singapore, University of Paris, IIC, and KTH in Sweden. His research interests are in information theory, game theory, and allied areas. So I think that is on the and let me just give a brief description of the logistics. So we'll have the session from 9:30 to 11, and then we'll have a break at 11, a coffee break at 11, and then we resume at 11:30. We'll try to stick to the schedule as much as possible. As far as questions go,
You can ask me anything.
yeah, so you can ask questions anytime. Request to the online speakers to keep their mics on mute unless they want to ask a question. And I think I'll hand it over to Professor for his talk. Thank you.
Thank you, Sudhir. Okay, welcome everyone. Online people, if you cannot hear me, you just send a message. I think this has been tested. Everyone should be able to hear me. If you have any questions, put your questions into the chat and I'll take them up whenever the volunteers point that out. Okay. All right. The topic for today is what I'll talk about is called strategic communication. Now, this is not some standard word. Okay, this is a word that many people are using in many different contexts. Uh, Unfortunately, I could not find a better word, so I've also used it. But the main I'll show you through this tutorial that what exactly I'm referring to. Unfortunately, we are at a sort of building stage of this field or this line of inquiry. So as a result, it's still not clear what all constitutes strategic communication, but there is a fair amount of idea of of the sort of spirit it must have. Okay. So to begin with, I want to first persuade you towards a certain view of communication problems. So this is your textbook information theoretic setting, which so this the topics here will involve some amount of communication and some amount of game theory, because this is SPCOM. I am assuming no background in game theory, but some amount of background in communication is something that we will begin with. Okay. So, but anyway, so here's your textbook, communication or information theoretic setting. You have M messages. There is a function f, which is called an encoder, that maps these M messages to a string X. I'm not putting that superscript X or N here, but that string is from an alphabet A to the N, where A is the single letter alphabet of your channel. So you get a vector here that goes into the channel. A vector comes out of the channel, Y. Then there's a function G that maps this vector, which is the function G is called a decoder, and maps it back to one of these messages. And we define this PE of n, which is the probability of error that is incurred by this particular code f and g. So f comma g is called a code. We define PE of n as the probability that what was sent is not what was received. Right? And you average this over all the messages. So this is the average probability of error. Now we define the rate of this code in the following sense. We define the rate of this f comma g as this log m by n. Okay, log m by n, which is the log of the number of messages divided by the uh, the log of the number of messages divided by the log of the codomain of this function. Okay, so this is log of m the divided by n. This is what we call rate. Now, the way information theoretic analysis proceeds is that we fix an r, and then we let n go to infinity and ask, okay, how does this particular probability behave? Okay, so you fix an r. Now remember, when you're fixing an r, you're not actually fixing either the domain or the codomain. You're fixing the rate at which the domain and codomain grow. Okay, so that is what is being fixed. You fix that, and then you let n go to infinity and ask, okay, what is the limit as n goes to infinity of this probability of error? Now this way of posing the problem is a somewhat non-standard in if you view it from a decision theoretic point of view. So in a decision theoretic problem, the space of your problem is fixed, and you have a certain cost that you are looking to optimize or you're looking to track. But here, on the other hand, in the information theoretic setting, the space actually keeps growing. So you don't actually have one problem, but a sequence of problems. The space keeps growing, and you are asking what is the performance of that sequence. So the decision theoretic way of formulating this problem would be that you fix n and m, okay, and then ask, okay, what is the minimum of this over f and g, and the limit as n tends to infinity. Now, this seems like a very, I'm just splitting hairs over this. No, it seems like a very minor point, but actually, once you pose this problem in this way, it becomes amenable to a certain line of analysis, and that's the thing that I want to take off from. So the point is, decision problems are always posed with a fixed decision space, and what you actually have in this information theoretic setting is actually a sequence of decision problems in this sense. So sequence of these sort of optimization problems parameterized by n. Okay. Now, and you can so what we know about this problem is this picture here, which somehow got cut off. So there is a number c up, such that, so if your log m by n is less than c, then this limit tends to 0. If log m by n is if the limiting value of log m by n is strictly greater than c, then this limit tends to 1. Okay, so there is this kind of phase change behavior that we see, and this C is called the channel capacity. Now, once I pose this problem in this way, because this now goes into what is, as I said, it's a decision theoretic problem, which means, so you look at this particular cost function here. So I can think of what you have here as a cost function, and this cost function then becomes a cost function of what is called a team decision problem. So this is the first thing that I want to point out to you. What is a team decision problem? So a team decision problem comprises of the following. It comprises of n agents, n decision makers, or n players, or agents, or whatever. There is a random variable psi which is called the environmental randomness, and it encompasses in it all the uh, randomness from the environment. Any kind of uncertainty due to noise or initial conditions or whatever, or measurement noise or system noise, all of that is put into psi. Okay? And it has some known distribution. Each player I has an action space. So the action space of player I is denoted by this calligraphic UI, and the goal of the player is to pick an action UI from capital UI. The information that the player has while picking that decision is denoted Zi. Okay. Now Zi is a function of this psi and u minus I. Now u minus I denotes the actions of other players in the system. Okay. So what is the goal of the player? The goal of the player is to choose the UI as a function of Zi. So the player I has an information Zi, and as a function of that information, he has to choose an action UI. And so the effect that this action has is that it goes into a cost function. There's a cost function here which depends on u1 to un and psi. And what we want to do is we want to minimize this particular cost function or loss function by choosing these functions gamma 1 to gamma n. Okay. Now, to the students in the audience, do I need to say more to make this problem well defined? Or is this enough? Sorry? What is the distribution with respect to? So the distribution is with respect to psi. See, each of these UIs is a function of psi comma u minus I. Right? Because they are a function of Zi. Zi is a function of psi comma u minus I. So the random variable in the problem is just psi. So the expectation is taken with respect to psi. So the distribution is whatever is the distribution of psi. Okay, good. Good. So actually, I need to say more. So that, and I need to say more because I need to respect causality here. Player I is taking an action. Still audible. Player I is taking an action as a function of Zi. Zi is obtained as a function of psi comma u minus I. So what you can have the following situation. If I don't put any restrictions, you can have the following situation. U1 depends on U2. U2 depends on U1. Okay. And neither of them can actually have well-defined random variables to define their information. Okay. So as a result, so you can get into what is called a deadlock, essentially, where each player has to basically depend on the other player to first take an action. And the whole thing is not well defined as a result because each feeds into the other. So these kind of equations for them to be well defined, you need to define some kind of a order of play. Okay. So and that order of play in a manner that it respects causality, so that the future does not affect the present and so on. Now there are a bunch of other conditions. I will not go into those details, but essentially, once I put in those conditions, then this becomes a well-defined problem. Now, why does this connect with this problem here? Well, I can think of these f and g as just gamma 1, gamma 2. Essentially, a case with two players. There are two players who are choosing these two functions, gamma 1, gamma 2. What is the noise, or what is psi here? Well, psi comprises of two things. One is the noise in the channel. The other is your the distribution of your source. In this case, the source distribution is uniform, the trivial distribution here, and there is the conditional distribution that I have written here is basically where your psi is hidden. Right? And what I have computed therefore is the expectation is a cost is some cost of this kind. So it's basically the expectation of some indicator function that this is not equal to that and so on. Okay, all right. And the another thing that I have implicitly assumed here is that all the gammas, gamma 1 to gamma n, are all chosen simultaneously, chosen jointly. Okay. Now, what does this mean that they are chosen jointly? Which means that it is possible for the end players to sit together, deliberate what is going to be each player's strategy. Okay, so defender says he's going to do this, attacker says he's going to do that, half field of players are going to say he's going to do that. Collectively, they decide these are going to be their strategies. But when they go into the field and actually play, when the ball comes to them, what they do, they have to act based on the information they have. So the action has to be chosen as a function of their own local information at that time. But the strategies can be decided jointly, can be chosen jointly. This is again reminiscent of what we do in coding. Essentially, you pick an encoding decoding strategy together in order to minimize your cost, and that's how your FMG is being chosen. Okay, so my point is, I mean, this is probably obvious to several of you, is that basically you look at a standard communication theoretic setting, and it is essentially an instance of a team theoretic setting. Okay, so the encode. So if you once essentially we are now thinking of encoder and decoder not as sort of chips, but rather as decision makers, and these decision makers are choosing, and their functions are their strategies. So this then brings me to this topic of strategic communication. So the strategic communication setting is where this last point is where we begin to depart from. So the players are not cooperating in the standard sense. Each player has a distinct objective of its own, and it may or may not involve communication in an explicit way. Okay, and hence the word strategy. Again, as I said, it's not a great choice of word, but I presently have no other name for it. Now, the point is when two strategic agents interact, okay, in a dynamic setting, whether they intend it or not, information gets passed between them. Okay, so when I am talking to you, I am actually trying to give you information, but sometimes I may be just talking to you, just like that, greeting you, how was your day, etc., etc. How that you get to know, okay, when did you arrive? Was the flight delayed? You come to know, okay, well, that it was raining in Bombay, there was traffic on the road, etc., etc. Some information gets passed between the sender to the receiver, right? So regardless of whether it is intended or not, communication is always happening. Communication in some form, okay, in the broad sense, is happening between sender and receiver. And the goal of strategic communication is to shed light on this. All of this, intended, unintended, explicit or implicit communication. That's what we want to do. And fundamentally, because these players are playing with a certain intent of their own, and the goal is not explicitly to communicate, it therefore demands a game theoretic analysis. Everyone good so far? Any questions? Any questions on that? Okay. Questions from the audience? Okay. All right. So as I said, I will not assume. I decided not to assume a background in game theory. So I'll give you some background, and then so hopefully till 11 or a little earlier than 11, we'll finish off this background. Okay. So here is an example of prototypical example of a game. So this is a famous example called prisoner's dilemma. Prisoner's dilemma refers to the following setting. You have two prisoners, A and B. They are each held in solitary confinement. So they are held in different cells, and they are each being suspected of a crime or accused of a crime. Now, they have been both given a choice, either to testify against the other player, say that the other player has committed the crime, or to stay silent. If both stay silent, they're both being essentially complicit in some sense, and neither is blaming the other. If one of them testifies, then the other guy is getting blamed. Okay, and we both testify, both are blaming each other. Now, here are the rules that the judge announces them. If both A and B testify, then each of them will get 2 years in prison. If one of them opts to remain silent while the other testifies, then the player who's testifying, the fellow who stays silent, is the one who's getting blamed, and he will get uh, uh, so the one who's staying silent he will get blamed. So the one who opted to remain silent will get 3 years in prison, and the one who testified against you, he will go free. If both of them remain silent, then each of them will serve 1 year in prison. Okay. Now we can debate about whether this is fair, which is not fair, and so on. But that is not our goal here. The goal is just to set this up and see where this leads. Okay. So this is then a kind of matrix that gets created. So each player the pair here written here the pair that is written here. You want me to wait for some time? Okay. So the pair of numbers written here is the number of years in jail for the row comma column player. Someone's phone. Someone's phone here. Let me just take him out. Okay. So yeah. So what was I saying? Yeah. These numbers here, I comma j, they basically reflect the number of years in jail that player I and player J would get, or player A and player B would get. So the first one here refers to the choices selected on the row. The second one refers to the choices on the columns, and both want to obviously get as few years in jail as possible. So we can sort of to begin, when you have a situation like this, you can ask this question in two different ways. So, first question is, you can ask is, what will each player do? Okay, what will each player do? That is the most natural thing that one would want to know. But unfortunately, we don't really know what will each player do. Okay, but we can ask a slightly different question, which is, what must each player do? So the what will each player do is a matter of prediction. Okay. What must each player do is what we think must happen as per theory. Okay. So that is the question that we want to ask. We want to ask what must each player do in the sense that if I can if is there a if I put in a bunch of rules, then as per those rules, what must each player do? Okay. And the entire the purpose of the theory of games is to come up with such rules, come up with such reasoning rules for these situations. Okay. So main observations from this: first, each player is faced with some kind of an optimization or decision problems there, but the decisions have to be made without the knowledge of the decision of the other. So these two prisoners were held in two different cells, unable to talk to each other. So they have to make that decision without this knowledge, right? So without the knowledge of what the other guy is deciding. But the outcome, the way the judge has decided, the outcome will depend not only on what one player does, but also on what the other player does. So their outcomes are necessarily coupled. So here's another example. So so this game comprises of two hunters who can choose to hunt either a deer or a rabbit. So they are both poised in to so you can say there's one hunter here, another hunter there. They're both watching a deer, and they can hunt that deer. Now, if both and as they are watching the deer, a rabbit runs by, and now they have this choice whether they want to hunt the deer or the rabbit. So if they both choose to hunt the deer, they can actually hunt the deer, and each of them will get half a deer. Okay, a deer is whatever worth 4, so each gets half a deer, um, and so they each get 2. If one of them opts to hunt the deer, if one of them opts to hunt the deer, then the deer is too big or too strong for one of them to hunt it. So then that fellow will get nothing. The fellow who went for the rabbit, though, he will be able to hunt that rabbit. Okay. So if one of them opts for the deer, the fellow who's going for the deer gets 0. The fellow who goes for the rabbit gets the rabbit. Okay, and he will get 1. If both go for the rabbit, then they each get half a rabbit. Half a rabbit is worth one, so each gets half. Okay, morbid story, but it's the but this is the situation. You have something. You have this deer that you can both of them can hunt. Obviously, uh, if they were to talk to each other and decide, okay, what are we going to do now that we have this situation, they would have both gone for the deer, right? Just like in the previous case, if the prisoners could discuss, they would both come up with the strategy to stay silent. But that option of communicating is not present in either of these situations. So again, we can ask the same question. So what will each player do and what must each player do? Again, we don't know what will they do. We've given two hunters. God knows what they'll do. Okay, but I can put in some bunch of axioms, some bunch of reasoning rules based on which I can come up with reasonable answers about what each player ought to do in this situation. So here, this is essentially the motivation from which von Neumann started. This is John von Neumann. So, and this is a quote actually from his book in 1944. When two or more rational decision makers interact, one would like to have a mathematical framework for reasoning about such situations under certain assumptions. Game theory is the study of such interactions involving strategic decision making. So a game comprises of the following. Then. A game comprises of a set of players. For each player, there is a set of strategies. Okay, a set of players is n. Each player I, there is a set of strategies. That set is denoted SI. There is an objective function, also called payoff or utility or whatever, that is uh, an objective function that is trying to minimize or a payoff function that is trying to maximize. So it depends on which community you come from. Generally, the in the engineering community, everyone's trying to reduce cost, whereas in the economics community, people are trying to maximize rewards. So this is just a matter of flipping the sign. But we will stick to minimizing. That's just more convenient for me. So an objective function ji is a function for player I is a function from S to R. Now what is S? S is the Cartesian product of the strategy spaces of all the players. So you have the set of strategies for player one times the set of strategies for player two, dot 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 till the set of strategies of player n. So you give me a tuple of strategies for the n players. That tuple defines for me gives me the information to define a payoff for each player. Okay, and each player is trying to get the minimum of their own respective function. So you have essentially n players, each of which is trying to optimize their own function without the knowledge of some parameters which are being chosen by another entity. Okay? So again, question for the students: what are the players' strategies, utility functions in the games defined before? For example, here, yeah, right. Correct. So this matrix tells you the payoff. You have to just read it off properly. The first entries are the payoffs for the row fellow who's picking the strategy on the row, say prisoner A, and the column play, the second entries are the payoffs for the prisoner B. Now in both of these examples, both players had the same strategy set. So the options were to stay silent or testify in this case, and the other player here also the option was to say deer, hunt the deer, go for the deer or to go for the rabbit. Right now, this is not necessarily always the case. This is the simplest case in which the physical strategies themselves are actually the same. But you could have both the players could have different number of strategies, or each player could have different number of strategies, and the strategy identities also could be different. Actually, after a point, you will realize that what the strategies are doesn't matter anymore. Whether it is what matters is what payoff they give. Right? Yeah. Yes. Good. So yeah. So what is known about this? So let's start with something like this game. So what do players actually know? They have been. I said that players cannot communicate with each other. Now, this means that player cannot communicate with each other during gameplay. Okay, they are aware, however, of what is at stake. So they are aware of this entire matrix. They are aware that what the options each player has at its disposal. We will come to a generalization where that is also not available, and that becomes a much more complicated model. I'll come to that in a moment. But that's the setting here. Okay. So the whole so we are building towards essentially the issue of information in games, and I'll come to that. Yeah. So just one last word of caution about what game theory is and what it is not. Okay, so game theory develops a framework for logically reasoning about these strategic interactions. And its attempt is to answer, okay, what do you think is the logical outcome of this interaction? Okay, so what I mean, the aspiration is to come up with a bunch of reasoning laws, just like you have the laws of physics. You put together, you start off particles in a certain state, you put in the laws that will tell you what the next state is going to be, right? That's the sort of ambition of game theory. It's in some domains it's still work in progress, but nonetheless here this is the ambition. That the attempt is to come up with a set of logical rules to reason about these situations, and attempts to answer what we can say is the logical outcome of the game, and about what we can in fact call an outcome. Okay, what should be the notion of an outcome is what we call a solution concept. You have to, okay, because there are these multiple optimization problems involved. There are more than one ways by which you can say something is a solution of this. Okay, so that is what is called, those are what are called solution concepts. Generally, the point of view taken is that of an observer of a game. Okay, we are not, doing things like putting ourselves in the shoes of the players and so on. We are just observing the game the way a physicist would observe a bunch of particles. It can be used for making predictions. In many applications, it has provided excellent predictions. It can be used for strategic and tactical decision making, strategic advice, prescriptions to players on how to play a situation, etc. It can be used to explain alter behavior or induce certain types of behavior. But this is what it can do, but it is not what it is what it intends to do to begin with. Okay. And what it is not is, here's an important thing, it's not a theory of human behavior, psychology, or any of this. It's just a bunch of reasoning rules. And it is not a secret code to win all the games you encounter around you or in any of that. Okay. So, yeah. So, all right. So, all the kind of games, both of these that I was referring to, are what are called non-cooperative games. The non-cooperative games means the following. Uh, it means that players have no scope for communication or discussion during gameplay. Okay, so they cannot discuss or communicate between themselves during gameplay. There is no mechanism available to the players for them for to get them into binding agreements. Okay, now, what is a mechanism like this that needs to be defined is essentially a uh, a, so I might be jumping ahead of myself, but it's essentially a mechanism to help to create a binding agreement a is basically a joint distribution on the strategy space, such that given what you have that recommends actions to each player. Okay, that's the more complicated definition of it. For the moment, let's leave that aside. So there is basically no mechanism for players to get into available to get players to say that this is what they are going to bind themselves to. So there is no way for them to say, for player A to say, for example, that I hereby certify that I will always play testify, or I will always stay silent, something like that. And then in response to that, the other player will say that, okay, I also testify that other player will I will stay silent, or something. So there is no way to come up with such kind of contracts between the players. Okay. So decisions, therefore, are in the absence of communication between players. Decisions are therefore made based on the existing incentives only. Okay. So this is essentially the situation. So these are what are called non-cooperative games. So the strategy of, so let's put in some more notation. So if xi is the strategy of player I, and x1 till xn is then the x denotes the strategy, the tuple of strategies. This tuple of strategies is what is called a strategy profile. Okay. X minus I, X minus I is comprises of the strategies of all, is the basically the strategy profile of all players except for player I. And so if I write x bar I comma x minus I, x bar I comma x minus I is this strategy profile that I create by inserting x bar I into its I into ith place, and everything else remains is chosen from x minus I. Okay, this is just a bunch of notation. Now the person here is John Nash, and what I want to tell you about is the solution concept that he proposed. So the solution concept, which is the solution concept, which is known by his name, which is the Nash equilibrium, is the following. So it is a profile of strategies X star such that the following situation condition holds, that no player has an incentive to deviate from that profile unilaterally. Okay, unilaterally means what? So unilaterally means that assuming the others stick to that profile, okay, assuming the minus I part of the profile is strategy profile is the starred value, player I prefers to stick to his starred value. Assuming the others continue to play what is there in the starred value, player I would go on to play his starred value, and this holds not just for any one player I, but all players. So, so a profile of strategies X star is a Nash equilibrium if no player has an incentive to deviate unilaterally. That means, assuming the other guys are not deviating, I don't want it. I have no reason to. Okay. Now, this is the solution concept that he proposed. He said basically, if we have a situation like this where you have n players, they are not allowed to communicate, there are no binding agreements possible, and so on. What can we make of this situation? He says the way we should be analyzing is that we should be looking for a point like this. This is what we should consider as the outcome of the game. Okay, so now why is this reasonable? I mean, this is, we cannot derive this. Okay, this is his what he proposed. We cannot we can derive the existence of a point that satisfies this, but we cannot derive the rules that he has prescribed, that a point should be satisfying these things. Okay, we cannot. So what we can only say is just what we can instead do is justify it, and we can ask, okay, why does it make sense? What is the justification? Well, so a Nash equilibrium is a profile of strategies where if any player I shifts unilaterally, he is worse off. Now, because you are in this situation where players cannot communicate with each other, you are in this extreme case where there is no communication whatsoever is possible. The only kind of deviations that are feasible are unilateral deviations. Any deviation in which more than one player deviates requires coordination, requires communication. Okay, so the only feasible deviations therefore are unilateral deviations, and therefore the you a basic necessary condition for any outcome is that there should be no more scope for unilateral deviations. If there was a scope for unilateral deviations, then that is not the final outcome. The play game, the reasoning process is still going on. Essentially, that is essentially the argument. So the Nash equilibrium is therefore a kind of a basic necessary requirement that any solution, anything that you want to call as a solution, must satisfy under these settings. Yeah. Yeah, why only unilateral shifts are feasible? It's because players do not have a means to communicate. Suppose if so, think of a more complicated situation, right? Like a few weeks ago, what happened in Maharashtra, for example. Okay, a bunch of players that were players led by a player called Eknath Shinde and another player called Devendra Fadnavis collectively decided to move away from the existing coalition that they were in, and then form a new government of their own. Now, this could have, for this to happen, the players have to talk to each other, right? So without this, it would not. So these kind of deviations are possible if there is a means of communication. Okay, so so collective deviations are feasible only under the assumption of communication. If there is no communication possible, collective deviations are not possible. And so therefore, only unilateral deviations are are allowable. And if only unilateral deviations are allowable, what it means, if anything has to be an outcome, it has to be the situation. It has to be the case that the player that what you have whatever is the whatever you're calling as the outcome has to be stable against such type of deviation. Otherwise, it's not the final outcome. Otherwise, the situation is still evolving. People are still in Guwahati or whatever, and in some hotel or so, and so on, right? So I don't know. I think people in Karnataka are not quite following. Okay. 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 So Nash equilibrium. Okay. So what is the Nash equilibrium for prisoner's dilemma? So it. Okay. Maybe I discuss. Anyone? What is the Nash equilibrium for the prisoner's dilemma game? So if no player has, if we want to look for a point from which no player would want to unilaterally deviate, both testify. So both testify becomes the Nash equilibrium for the prisoner's dilemma. The reason is simple that if you look at any of the other points, in this case, you can just do it by elimination. You can look at any of the other points. You will see, say, for example, one fellow stays silent and the other guy testifies. Then, if the other fellow is testifying, I would not want to stay silent. I would also want to testify. So then, therefore, silent testify or testify silent is never going to be a Nash equilibrium. Likewise, both staying silent is also not a Nash equilibrium, because if the other guy is staying silent, I would want to testify because I'll go free, right? So silent, except for silent is also Nash, not a Nash equilibrium. Now this eliminates the others, doesn't mean that testify is a Nash equilibrium. Okay, it just eliminates that the others are not. But you can check that testify is actually a Nash equilibrium and the only Nash equilibrium, because once the other fellow is testifying, it's optimal for me to testify. I would not want to stay silent in that case. Okay. What about this deer rabbit thing? This is somewhat more complicated. Both what? Sorry. So here, yeah, here they are looking for the maximum reward. They were looking for minimum number of years in jail. So they are looking for the largest number in the matrix. So if you see here, the pair deer is a Nash equilibrium. Rabbit is also a Nash equilibrium. The reason is, if the other guy is going for the deer, this guy say maybe Atom will both hunt a deer. Okay, so they'll both hunt a deer. And if the other guy is going for the rabbit, okay, it doesn't make sense for me to go for the deer because I will not be able to take the deer myself. Okay, so I will continue to. So then, therefore, rabbit as well as deer are both Nash in this case. And the other one, which is deer rabbit or rabbit deer, they are not, because if one fellow is going for the deer, the other, it makes sense for the other guy to also. Yeah. So what if I go for deer and the other one go for rabbit? I will be on the low side. Yeah. Yeah. So are you saying is there are what happens because of both being Nash equilibrium? I'm doubtful of deer being in. So there are, yeah. So this is no, they are Nash equilibria. Whether they can be improved on is a separate question. So this comes to a topic of what is called refinement of solution concept. So Nash, as I said, Nash equilibrium is sort of, you can think of it in one way as a bare minimum requirement. The bare minimum requirement is no unilateral deviation should be possible, because otherwise as I said, your deliberation process has not settled. Okay, the the if you can of course ask, okay, now that you are in this situation where there are multiple Nash equilibrium. So there is deer is also a Nash equilibrium, and rabbit is also a Nash equilibrium. Which of these, amongst these, which is sort of in some sense a better Nash equilibrium? Okay, or can we put in more axioms than what Nash put and say, okay, I put in more demands and say, well, can I eliminate some of this and come up with an even sharper answer where maybe only one point will remain? That is what is called the process of refining a Nash equilibrium. It's a topic in itself, but it's a very slippery topic. There are refinements, and you are right. If in a certain type of logic, the rabbit will turn out to be the rabbit will turn out to be the one that the one that remains, and that way of refining is it basically involves looking at the risk of, suppose if you know this thing that you are saying, what is the risk involved if the other guy doesn't stick to deer? Okay, then in that case it would be better off for me to shift to then better off for both to shift to rabbit. Okay, that's it requires that kind of thinking. Now what is risk, what how do we measure it, and so on, is a completely different set of analysis. Essentially, if you want to put in any more axioms, you have to make sure that those are universal, in the say just like Nash's axioms are universal. All of those axioms should also be just as widely applicable to all situations, and then in the situations of interest where these kind of problems occur, they should give the prediction that you are trying to propose. This is essentially what needs to be done, and people have made efforts like this. So one kind of way of thinking about it will lead you to rabbit. Another kind of way of thinking, which is a simple way, is to simply say deer is better, because that's better, uniformly better for both. So in some ways it dominates, right? So that is actually a better for both, and then that way, then that is also can be argued. Okay, so we leave it at the level of the Nash equilibrium, because from there, beyond there, that point, actually it starts getting into a territory that needs a lot more sophistication. So let's not get into that right now. But yes, it is possible to argue along those lines. Okay. Yeah, so this is, I just mentioned that non-cooperative games means no communication is allowed and so on. So yeah, so I've just argued about this. Okay, so now let's go to okay. Any questions so far? Oh, okay. Any other questions from the audience? Okay. All right. So this is so here so what we have done is, so far we've just said players have to pick a strategy, right? But you can give players a bit of some additional resource, then, in order to try and improve their payoff. Now, so this simple resource is to do local randomization. The resource is just local randomization, which means that instead of picking a particular strategy, what they do is they choose a strategy at random. But random doesn't mean with an arbitrary distribution. They actually choose their distribution wisely. So the strategy then becomes not to choose a particular strategy, but rather choose the probability distribution with which each strategy is going to be chosen. Okay. So for now, this is going to be my notation throughout the talk. So let S, for any set S, let P of S denote the set of probability distributions on S. Okay. Now we will call what I was earlier calling strategies, we will now call them pure strategies. They are what are called pure strategies. And once you and the elements of P of Si, they are called mixed strategies. Okay. Mixed strategies is basically a probability distribution on the set of pure strategies. So, and in mixed strategies now, what we need to do is the following. So if players are going to choose their pure strategies, these small SIs at random, so now these become random variables distributed according to the distribution. So the distribution so the probability distribution chosen by player I is denoted gamma I, and so what the player should now do is compute the expected payoff that he gets, assuming he plays gamma 1, gamma I, and the others play gamma minus I. So this is the payoff, the expected payoff of player I as a function of the profile of distributions chosen by the n players. Okay, so the expectation is computed over this. Now, how is this expectation computed? So as I said, these S1 to Sn are now random variables distributed according to this, but gamma I only just tells me the marginal of Si, right? So if you want, so to compute the expectation, what we do is we just take the joint distribution is taken as the product. the joint distribution of S1 to Sn is just taken as the product of gamma 1 of S1 till gamma n of Sn, and then you just do this summation. Okay. And now we have essentially just elevated the problem to a different set of strategies. Strategies are now not specific choices like playing deer, playing rabbit, but rather with what probability am I going to play deer, with what probability am I going to play rabbit, and so on. Okay. So you can now again talk of a Nash equilibrium in this space. Okay, the Nash equilibrium in this space is then is just defined as before. So the expected payoff now has to be, so each player has no incentive to deviate unilaterally from his own chosen distribution, assuming the others stick to their mixed strategy or their chosen distribution. Now, how do you interpret this kind of these kind of gammas? So you interpret them in the following way. One way is to say, well, this is deliberate randomization that player is doing, and that is an interpretation that can be given. I can give you some examples and so on. Another way is to say, well, he actually has. So suppose this player is say a general. You know, he has 1,000 people, but he has 2,000 soldiers, but he has two posts to defend. He has a post, one post here to defend and another post there to defend. A pure strategy would mean to send the entire troop either here or the entire troop there. Another way would be say, well, okay, 400 of you go here, 600 of you go there. You know, that division of resources is another way of interpreting this kind of this sort of strategy. Of course, there are some caveats involved. Things may not be linear with that division and so on. But under that kind of assumption, this works. Okay. Another way is to what people do in finance all the time, which is the diversification of portfolio, which is that instead of putting all your eggs in one basket, or instead of putting all your everything's still working, no? So instead of putting all your instead of playing a particular strategy, you diversify over those set of strategies that you have. That's the how to diversify and the probability distribution that you want to put in that is essentially what is being encoded in this gamma. Yeah. Yeah. So a good question. I was about to ask. So why product distribution? Okay, so Vaibhav has seen all my slides. So why the product distribution? Sorry, independent. But why independence? No communication. No communication. See, that's the important thing. So if you so the if there was communication, so if you want to get a joint distribution, that means there is shared randomness. Okay, and the shared randomness is going to come from is going to come because of communication. Now, so this becomes again a more involved matter, and it could have become a topic of a different tutorial. Essentially, what are we referring to by communication, and communication between whom and so on. So players may not be able to communicate with each other, but may be able to communicate with a third mediator. Okay. So then through that mediator, correlation can be created. Okay, and so really what we mean by communication is a fairly wide question, and then what is the capacity of the channels that allow this kind of communication and so on. Those is the whole can of worms. But anyway, but simple setting that I'm talking about right now on this slide. Later we'll generalize, but right now on this slide is that we have we have a product distribution here because players cannot communicate. So then therefore the joint distribution is the product of marginals. Okay. So now, what is the point of this particular thing of moving to this space? One is that, of course, you are enlarging or enriching the space of strategies that players can play. But the other thing is that actually we get a mathematical result. So first result is this major milestone actually in the theory of games, which is von Neumann's min-max theorem. So this refers to the setting where there are just two players and what is called a zero-sum game. Zero-sum game is where the costs basically add up to zero. So there are just two players. So the other fellow's cost is equal to your negative of your cost. Okay, so J1 is minus J2, and they are each denoted. So J1 is denoted by J, the other is minus J. Okay, So what is you can think of as happening is that there's one function j. Player is just looking to minimize this function by choosing s1. Player one is looking to minimize this function by choosing s1, and player two is looking to maximize this by choosing s2. Okay. Now, and then again you define the expected j as a function of gamma 1, gamma 2. And by allow make again this is with the product distribution. Sorry, there shouldn't be a j1 here. It should be j itself. Okay, that's j. Okay. Now, what is what Neumann's min-max theorem? So let s1, s2 be finite. Okay, and j be anything. If s1 and s2 are finite and let j be anything, then what he shows is the following. He shows that there exists this profile gamma 1 star comma gamma 2 star. Gamma 1 star is a mixed strategy of player 1. Gamma 2 star is a mixed strategy of player 2, such that if each guy plays his star strategy, I would not want to deviate from my star strategy. So assuming the other player plays his star strategy, what you're going to get is j bar of gamma 1 star comma gamma 2 star, and the maximizing guy would want to stick the minimizing guy would not want to deviate from gamma 1 star, and the maximizing guy would not want to deviate from gamma 2 star. This is what is called a saddle point. Now, so you can see this saddle point is actually is essentially a Nash equilibrium, but stated in a slightly different language. Now this so what von Neumann's min-max theorem basically shows is that if S1 and S2 are finite, there is always a saddle point, provided you allow players the opportunity to play mixed strategies. Now, if you can ask, okay, is the games that I showed you, there was a Nash equilibrium in for both those games, but there are games for which there isn't even a saddle point in pure strategy. So the big impact of this theorem is that now, regardless of what the game is, there is always a point for us to work with as a solution. If you did not have, if there was no saddle point in pure statistics, you would not even be able to proceed further with the analysis, because you would say there is no there's no mathematical point that satisfies the solution axioms that I have. But for now, if you allow for mixed strategies, however, there is such a point, and with almost no questions asked. Essentially, if S1 and S2 are finite, there is a mixed strategy saddle point. Okay. So, and then moreover, there are all these nice properties also. So, for example, if you have two saddle points, so here, provided I've not made any typos, my superscript will always denote the player, and subscript will denote the index of is some instance of some other index. Okay, superscript always stands for the player. So here, gamma superscript 1 sub 1 is player 1 strategy 1. Superscript 2 sub 1 means player 2 strategy 1. Okay, so this here is one saddle point. This here is another saddle point. Now, if each of these are saddle points, you can actually, do sort of mix and match. So you can take this one from gamma one, and this one from player one, and this one from player two. So gamma 1 1, gamma 2 2, that also is a saddle point, and gamma 1 2 and gamma 2 1 is also a saddle. Okay, this is called the interchangeability of saddle points. So you can the saddle points. So this is also another nice thing. So one of you asked me right now that what if I don't know what the other guy is playing? Right? He could be playing this, he could be playing that. In the zero sum game, it doesn't matter. Regardless of what he's playing, I'm still going to get a saddle point. And in fact, all saddle points actually have the same value as well. The J bar, so this value is going to be the same irrespective of what saddle point I put. Okay. So this is therefore a major milestone in the theory of games, that we set up this kind of reasoning rules and said, okay, this is how players should play. We found, but with pure strategies, we may not be able to solve. But if you allow for this additional resource of local randomization, there is a solution, and therefore we can now proceed with analysis. Okay, so it was later observed that this is actually equivalent to linear programming duality and so on, which came much later. Yeah.
Min-max equality. But I think
Yeah. Max min is equal to min max, no? That can be shown. I'll need a It'll be a digression. Can we do it in the break? I'll show it in the break. Yeah, it's essentially you can. It's just this. Um, so what you need to. So here this you have. Mm, so this minimum. Yeah. So what you can do is the following. Okay, here I can just give you a quick hint at this, and then we'll complete it in the break. So you look at these two extremes. Okay, leave the thing in the middle and just look at these two extremes. Now what you have is a function here of gamma 1, which is always above another function which is of gamma 2. All right. Now, what this would mean is that, yeah, so minimum overall gamma 1, and here I can do maximum overall gamma 2, will always have max over gamma 2 of this is less than equal to min overall gamma 1 of this. And I think from here you should be able to argue that the order doesn't matter. Okay, yeah. So I can argue that here. Let me see. Sorry, I just you have these two extremes, and this in turn is less than equal to um, max over gamma 2 of the same quantity, and this here is less than, greater than equal to min over gamma 1 of the same quantity. Okay, and this holds for all. So maybe I'll not confuse you. I'll just put a gamma bar here. This holds for all gamma 1, gamma 2. Right? And now you can take the so now you can take the min, you can maximize this over gamma 2. So you will then say max of gamma 2 here, and then you do the min of over gamma 1 here, min of gamma 1 of this, of the max over gamma. So you get max min is less than equal to min max, and that is, and whereas in general the opposite actually goes. This actually gives you the opposite direction of the inequality. So in general min max is less than equal to max. No, this is essentially the anyway. I can complete that in this thing. So this is essentially the idea that the saddle point inequality. So one of them holds directly, and the saddle point inequality flips what you need to the thing that you need to get. Okay. So at 10:30, okay, we can. Yeah. So this is so one norm is min maximum. So historically, why do we mention this? Because historically, actually, this came first and it has a special place and it has some special properties. So this is around the 1920s or something, uh, and but you see the what happened was actually during the development of the theory of games, the people were too occupied with this sort of thing, interchangeability and so on, all these peculiar specific properties that came from the two player zero sum setting. And what was lost is the fact that there is an angle of communication involved in games. So when you have two players whose objectives are opposite to each other like this, right? There is nothing for them to correlate on. Because whatever one guy is out to kill you, the other guy is out to kill you, right? Whatever you do is whatever any profit to you is lost to him. Okay, so there is no scope for both to sort of collaborate or jointly work or sort of communicate and so on. So the entire angle of communication was actually lost because of this specific setting that was being considered. So Nash's main insight actually comes by saying that, well, you take non-zero sum games where the games where there are n players, the payoffs do not sum to zero, and which means that there is a scope to selectively cooperate or compete. So you may selectively want to testify or may want to stay silent, and that dilemma that is present, which is essentially the dilemma in the prisoner's dilemma, is what he tries to he says he basically shed light on, and he basically said that the role of communication is very important in this setting. If you do not allow players to communicate, you would have one type of solution. If you allowed players to communicate, you would end up having another type of solution. So this thing, what I've talked about so far, is the non-cooperative setting in which communication is not allowed. And so here, so so Nash's theorem is basically this. That so you again, your n players, player I chooses his mixed strategy gamma I to minimize his expected payoff, and he shows that although there may not be a Nash equilibrium in pure strategies, there is always a Nash equilibrium in mixed strategies. And this is then a significant generalization of von Neumann's min-max theorem. Von Neumann's min-max theorem is a special case, and it's actually in some ways misleading also, because it sort of tends to sort of point to a lot of other type of phenomena which don't happen more generally. Okay. So the theorem is basically this: let Si be finite for each I, then there is a profile of strategies like mixed strategies, which is a Nash equilibrium. Yeah.
So here, this mixed strategies are a subset. No, pure strategies are a subset of mixed, right?
Yeah.
And there is no condition of SI.
Finite, just finite.
It
Yeah.
should be group or pure strategies.
No. 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 It doesn't happen like that. But the reason is because uh, you are looking for this kind of a fixed point type of condition. Assuming the others play mixed, it's optimal for me to play a certain mixed strategy. So me mixing forces the other guys to mix, and the other guys mixing forces me to mix. That's what happens in a mixed strategy naturally. It doesn't imply you you so for example, assuming the other guys are playing some mixed strategy, I will always have a pure strategy which is my best choice. But that best choice pure strategy is not going to be a Nash equilibrium, because it will not force me playing that will not force the other guys to play that mixed strategy. So everyone randomizes and sort of tries to fool each other or whatever you want to call it, and that leads to an equilibrium. And that does not necessarily translate to a pure strategy Nash equilibrium. Yeah. Mm. No, no, that's not. I think what Vaibhav is talking about is slightly more detailed point there. Is it uh, so this base? Yeah. So of course, the existence of a mixed strategy here only does not reduce to a existence of a pure strategy, and there are counter examples.
Here the mixed part is captured when
So it's in this distribution,
right.
and
Distributions can be degenerate.
so that in that case it would be. In that case it would be.
Here that should not be a degenerate.
No, 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 no. This is the only thing we can guarantee is that there exists something in this class. Now it may be degenerate in some cases. Like if I solve this for prisoner's dilemma, it will turn out to be degenerate. Okay. But if I solve this for the deer rabbit, I will actually get three Nash equilibrium. I will get my pure strategy Nash equilibrium, deer deer. I'll get a pure strategy Nash equilibrium, rabbit rabbit, and I will also get one mixed strategy one, which is neither of these two.
So it depends on what actual strategies are.
Yeah, 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 yeah.
You're right. We are putting a constraint on the SID.
Hmm.
In the earlier game, the
I
constraint was not there.
no, it's there. Yeah, yeah. It's there.
Even if it is infinite, you will still get.
Yeah, yeah, yeah. So this is just the, as I said, that's why it's introductory. There are much more general versions of the same thing. Yeah, so you can go to LP spaces and all that also. It's very, very, many much more general versions are there.
Infinite thing would work for the limit theorem, but it wouldn't work for mathematical, right?
Yeah, the proofs are harder. I mean, the result, of course, for infinite, there is what is the most general I know of is what's called Kiefan's inequality, which which works, I think, some Banach spaces or something very general setting.
This is not true in general. This result is
Yeah, I mean, depends on how general you want to be. I think, yeah. So you need, so for example, one of the things you need in the more general setting is convexity. Okay, that J bar has to be convex in the minimizing variable and concave in the maximizing variable. Okay, that is something that is needed for more general results. Here, because it's linear, that that is sort of glossed over, that whole point. Yeah.
is from following bullet 1 in slide 13.
Hmm.
For n greater than 2, in case of mixed strategy, given that there always exists a saddle point, in general, what can be the max number of saddle
Max number of saddle points. Yeah, I don't know what is the maximum number of saddle points. It really depends on the matrix at hand. I'm not aware of any way of saying how many saddle points are there.
That's the only question.
Sure. Any other questions from the audience? Okay. Okay. So now with this, we will go to this whole issue of information in games, and I think yeah, I think we are doing okay time wise. Okay. All right. So all the above games that we talked about, and this was a sort of a warm up, were games where players moved simultaneously without the knowledge of the information what the other player does. And so this is, so once we bring in things get very interesting once we bring in you know that allow once you bring in the fact that players are playing dynamic, or there are players are playing in sequence, and then there are issues such as information and commitment and so on will show up. Okay, so here is one example. So suppose, so so let's take this setting. You have the game starts with this in this node X. Okay, this is where player one is going to play. Player one has two strategies. He plays either left, or L1 or R1. Okay, left one or R1. Now, if he plays L1, the game goes to node Z and the game ends. There's nothing for player 2 to do there. The game ends there. If he plays R1, then the game goes to node Y, where player 2 will now take over. It's now his turn to play. Player 2 has two options to play L2 or R2. Okay? And the payoffs are now listed at the, you get, the payoffs get accrued in this kind of a setting at the end. Okay, at the end of all of this. So if the game has gone to node Z, then the payoffs are 0, 2. If it goes to this particular node here, payoffs are -1, -1. If it goes here, it's 1, 1. And here players are trying to get the maximum number. Okay. So just, sorry, I should have flipped this. They're trying to maximize. Okay. So now what are the strategies for the players? So for player one, what are the strategies? L1 and R1. Simple. Right? He has to choose either L1 or R1. What about player two? Hmm? Hmm. So you can say there is basically a fictitious sort of do nothing strategy here. Okay, for player two. Okay, so if player one has played L1, he does nothing. If player one has played R1, he has two choices, L2 or R2. Okay, good. So then what are the Nash equilibrium? Hmm. R1, R2 is an Nash equilibrium. Why? Because R1, R2 leads to 1 comma 1. Okay, both players are going to get 1. Player 2, in that, if player 1 is playing R1, player 2 would not want to shift to L1. Sorry, player 2 would not want to shift to L2. Okay, because otherwise he'll get minus 1 in place of 1. And likewise, player 1 is playing R1. He's so if he shifts from, so since player 2 is playing going to play R2 here. Okay, player 1, instead of playing R1, if he had shifted to L1, the game would go here. Okay, and in which case he would get 0 in place of 1. Okay, so R1, R2 is a Nash equilibrium. Correct. Any other? Okay, L1 do nothing is a Nash equilibrium. Why? Hmm. Okay, so once player 1 plays L1, it's obviously optimal for player 2 to play do nothing. But what about player 1? Player 2 doesn't have a choice, so he does nothing. Okay, but what about player 1? When would player 1 actually play L1? Hmm. Hmm. Yeah, so what is actually the Nash equilibrium? So this is deliberately I have chosen this particular thing to start off with because I want to I want you to sense that there's something ill posed going on here. So L1 do nothing is okay now, but why would player 1 stick to L1 is the question rather than shifting to R1? You may say, well, player 1 will stick to player 1 will stick to L1 because player 2 is going to do nothing. But then, what if he shifts to R1? In which case, he could do something. You could do that, but I think that's not necessary. Okay. So actually, now what? Mm. Right. Mm. Mm. So good point. So if play so here now in this kind of a setting, firstly we have to be careful about what we talk, what are our strategies. So once we have defined the set of strategies for the players, then we can talk of things like Nash equilibrium and so on. So what did you say as other strategies for player one? Very simple, L1 and R1. For player two, what are the strategies? Now, the assumption here is player two knows that what player one has played, which is why he is going to act only when the game comes to Y. When the game comes to Z, he is going to do nothing. He can see what player one has done. He has whatever observation medium he has. It tells him what player one has done. Now, and he knows at Y that it is his turn to play. And then he says he's going to play either this or this. So the strategies for player 2 are not just L2 or R2. Strategies for player 2 are a function of what he knows. A function of an action which tells him what he should be uh, it's a function that tells what action he should be taking based on what he knows. Okay, so so therefore the function for the strategy for player 2 is conditional on what he knows, right? So it is do nothing if p1 has played l1, or one of two possibilities, either play l2 or play r2 if p1 has played r1. Okay, so it is a function of what he knows. So the strategy for player two is not just a particular this thing saying that okay play L2 or play R2. Okay, it is this function. One second. So therefore, now in this case, now because now I am expanding my definition of what we call strategies. Strategies now are not what we were earlier saying, this deer, rabbit, whatever, those were our strategies. Now those we will call them as actions. Actions are something that will directly go into a cost function and give you a cost. Those are called actions. Strategies are functions that decide the action based on the information you have. Okay, so now, so all these L1, L2, R1, R2, and do nothing, these are actions. Okay, and the game has actually two Nash equilibrium, as some of you alluded to. One is of course very simple, R1, R2. So what does this mean? That if player two is going to stick to playing R2 here, player one has to stick to playing R1, and likewise player one plays R2, play R1, player two will respond with R2. That's one Nash equilibrium. But there is also another Nash equilibrium, like Sudhir said, which is this L2 L1. What do I mean by this? The strategy for the so just let's first actually just look at why I'm saying it's a Nash equilibrium. So if player two promises to play L2, okay, if player two is going to play L2 here, okay, then what is going to happen? Both players are going to get -1. If player 2 plays L2, both players are going to get -1. Then player 1, knowing that he's going to get -1 here, would never want to play R1 because he will because he if he gets if he plays R1 he's going to get -1. Instead, what he will do is play L1 and take the game to Z, and then finish off the matter there. Player two doesn't have a choice to act there. And player one will get 0. This is better for player one to get. He gets 0 here, and here he was getting -1. So if player two promises to play L2 here, if player two is going to play L2, it's optimal for player one to play L1. And then what about player two then? If player one is going to play L1, okay, if player one is going to play L1, player two has no other choice. He has to just play do nothing. But coming back to the question I asked, why did player one choose L1 in the first place? He chose L1 in the first place because player two made this promise of playing L2 at Y. But by promising to play L2 at Y, he basically drove the game to Z, in which he had to actually not play anything. And guess what has happened actually? If you look at the numbers, player 2 has actually come off better off here. He's got 2 here as opposed to -1, which is what he would have got in L2. So we can interpret in these two equilibria in the following way. So R1 and R2 is essentially, can we lock that? So R1 and R2 are R1 and R2 is what we call subgame perfect. Subgame perfect means the way you reason about R1 and R2 is you can start like dynamic programming, start from the last time and say reason backwards. Well, if I was here, what would I do? What would player do? If he was here, he would play R2. And then knowing that player 2 is going to play R2, player 1 will play R2. Right? So you would get R1, R2 through that reason. But that is not the only equilibrium. There is also another equilibrium here in which player 2 is basically issuing this threat. If you come to L1, if you come to Y, I'm going to play L2 and I'm going to give you a -1. And then player 1 in response to that doesn't actually go to Y, he takes the game to Z. Okay, so there is this, so this therefore is called a threat equilibrium, there are many other names for it. But so essentially this is also an Nash equilibrium. Okay. Now, how do we write this out formally? I'll just tell you. Here is, let's take this even, make this even, yeah.
The minor matter. So what you're referring to as an equilibrium is a tuple of strategies rather than a tuple of actions. Right?
Yeah. So I'll come to that. Next I'll define this. So this what we just saw is an example of a dynamic game. Okay. Now here is another one, and we will now I can more formally write out what are the set of strategies for the players. Okay. So here's another one. Player one is playing has three choices: L1, M1, and R1. Player two, okay, player two plays next, but he cannot distinguish between whether player one has played M1 or R1. So he has some imperfect observation device which only tells will only give him a correct reading if player has played L1. In that case, he will know that he's played L1. But otherwise, he will not. He will only know if player one has not played L1. He will not know whether he's played M1 or R1. Okay. So we put these nodes in this kind of a box. This is what is called an information set. Okay. An information set. So it means that these the set of if you enclose nodes of a player in an information set, it essentially means that all those nodes are player has no way of distinguishing between individual nodes in that information set. So these here, so player two has no way of distinguishing between these two. Okay. And now a player has to now choose an action based on the information that he has. So the information set here is essentially is sigma algebra or whatever, and as a function, so for each information for each information set, he has to pick an action. So now a player is must choose the same action for every node in the same information set. Why is this the case? He doesn't know which node. If he had the technology to take two different actions in two different nodes, then he basically means that he could distinguish between the nodes, right? So he's obligated to take the same action in both at all nodes in the same information set. So essentially now his strategy now are functions that map his information sets to actions. Yeah. Proper meaning was? Yeah. Yeah. I don't know what the difference is, but yeah, it's a function of the information set. Means you may not have a formula. I mean, but it's a map. I'll just write it down here. So strategies now are functions that map information sets to actions. Okay, singleton nodes are trivial information sets. And the games of simultaneous play that we have seen so far, like the prisoner's dilemma and so on, are those in which the player has only one information set. Essentially the information, there is nothing. Basically, he has no information. He has no way of telling what the other guy has done. So these information sets are basically ways for us to encode the information that players have during gameplay. Okay, and so as a result of that, we can write out these strategies for the player. So the strategies for player one are simple: L1, M1, R1, because he has only one node and one information set. Strategies for player two are now mappings from his information to actions. So you can write it out like this. So gamma 2 is equal to L2 if player 1 plays L1. That means if he is here, he plays L2, or if he is at one of these, if player 1 plays M1 or R1, he plays U2. Say, for example. Another strategy is play R2 here and play U2 at this whole information set. I don't need to say further, because these are both nodes in the same information set. So it has to be the same action at both. Likewise, here's another strategy, which is play L2 here or D2 at this information set. And then here's a fourth strategy, play R2 here and D2. Is this clear? So now you can write out so this now becomes his space of strategies. Okay. So you can now write out basically, once you plug in the strategies for each player, you can basically set of strategy. If you give me a tuple of strategies, it will define for me a definite path through the tree, which will end at some leaf node. And at that leaf node, my payoff will accrue, right, for all the players. And so I have my payoff, therefore, defined through that. So it will be J, and now in this space of strategies, I can define a Nash equilibrium. Okay, in the space of these functions. Each player is picking his own function from his information sets to actions. And a Nash equilibrium is a profile of functions like now, gamma 1 star to gamma n star. This is a Nash equilibrium if, if this holds. Assuming the others play their minus the star value, I would not want to deviate from my choice of my function. This clear? Okay. So this is called a Nash equilibrium in a dynamic game. Yeah.
Player say information sets will be exclusive.
Exclusive means
Can it happen that a player, if you have the previous slide, then you know by case that either the player one has played L1 M1 or M1 R1, but you don't know it is exclusively only.
so you if you have a situation like that, you can, this is a modeling device. Okay, so if you have a situation like that, that it's either this or that, you can try to create another tree in which this is reflected. Okay, so in this sort of situation, what you have is there is some uncertainty about whether it's M1 and this or M1 and that, right? No, no, no. So the way we do, so that thing, there is another variable, a hidden variable, which is contributing to this uncertainty, whose value you do not know, and then you include that in the tree, and then you will get two disjoint sets like that. So information sets cannot intersect. Okay, they are partitions of your the player's nodes, and you cannot, they create a partition on the set of on the nodes of the player. They cannot intersect. Modeled into a tree like that. Yeah, yeah, yeah. You can create, you can use this to use this framework to model. Okay, so I okay, I think I'm a little short on time. Let me complete this and we will. Okay, let me complete this concept, then we will take a break. Okay, all right. So here now, okay, now this I wanted to pay attention to in this. So the way we reasoned about Nash equilibrium is we said, well, it's a pure a tuple of strategies is a Nash equilibrium because we don't want, we are preventing unilateral deviation, right? Now, what one of the things that happens in a dynamic game is the kind of thing you saw here in this thing, right? That it, I use this word that for this L1 L2 equilibrium, the threat equilibrium, I use the word that player 2 is promising to play L2. What does it mean to promise to play L2? So what is this thing of promising to play L2? This promising to play L2 means there's a new angle that has come up in a dynamic game. So players may have a certain sequence of play. Okay, it's your turn to play, then my turn to play, then some other, and so on. That is the order by which you are supposed to play. Okay, but a player can make a commitment out of turn. पहले से just shout, I'm going to play this, and that actually is a strategic device, to pre-commit to a particular strategy. So there is a new angle that emerges once there are dynamics in a game, and that angle is that of commitment. That's the thing. So if you suppose, let's take the case where there are two players. Okay. Now, if player one commits to a strategy first, regardless of whether he is actually the first one to act, okay, he can just announce, whatever you guys do, I am going to be doing this. He announces that to everyone. Okay. That once you allow for that kind of a device, then that changes the strategic implications for the other players. Okay, so if a player can commit to a strategy, so suppose player one commits to a strategy and announces it. Now player two has to then respond as a function of that strategy. So the strategy that he chooses has to be, now he also knows that the other guy is going to play this. Okay, so knowing that the other, when player one has committed to gamma one, player two now has to play what we can say is his best response. So he picks his gamma two to minimize his cost as a function of gamma one. And now you can reason from the point of view of player one. Okay, how is player one thinking? What is this business of shouting out your strategy? This whole business is basically what he's doing is he's anticipating the response that this will result. Okay, so he looks at the response that it results in, and knowing that this will result in a certain response, he is making his commitment. Okay, so this leads to a concept of what is called a Stackelberg equilibrium. So player one makes a commitment, anticipating the best response that will result from from player two knowing this announcement. Okay, that's called a Stackelberg equilibrium. Now let's read through this. So what player one is trying to do is basically minimize his J1 over gamma one, but there is this additional term here where he's doing max over gamma two over gamma two lies in the best response to gamma one. So he's looking at all possible best responses that player two could respond with, looking at the worst case of that, and then minimizing his cost with respect to it. Okay, so that's effect. So he's thinking of the behind the announcement is, if I'm going to make an announcement, player one could then respond with one of these three things. Let me make an announcement that in the worst case, that will give me the best job. Now, this worst case thing is a little bit of a problematic thing because it's a loose, it's just like that. You could buy worst case, you can take best case, you can take some other this thing and so on. So there are variations here possible. But this announcement as a strategy, like pre-commitment as a strategy, is an extremely important device. Okay, and you will see this, like for example, you are trying to plan some trip or something like that. Someone fellow, I will go whatever you want. I'm going to Goa. One fellow will just and then others will have to then, as a response to that, because this guy is stuck on this, he will others have to respond to this particular thing. Okay, so this leads to this new different concept of different way of solving it. It's called the Stackelberg equilibrium. So essentially the leader is anticipating the best response of the follower. This is different from Nash. In Nash you don't have this as a function of gamma 1. It's a function of gamma 1 star, which is his Nash equilibrium strategy. Right? Here it's a function that response is anticipated. And so important thing also as a okay, so it's okay. I'll just last slide. I'll finish it off. So another thing that happens here is that because of this, unlike in the Nash equilibrium where there was the order of play had no relevance, right? Here the order of play is order of commitment matters. I commit first versus you commit first will lead to two different Stackelberg equilibrium. The solution will differ. And as I said, order of play is different from order of commitment. You may be the first one to act, but you need not be the first one to commit to a particular strategy. So you are just committing a function. Okay. And you can check here that L1, L2 are both Nash equilibria. R1, R2 was actually is a Stackelberg equilibrium if player one commits first. Okay. Yeah. Yes. So now once you are in dynamic games, a lot of this communication thing will open up. I was about to say that in the next slide. So here there is so we are allowing here in the Stackelberg equilibrium, we are allowing the facility to pre-announce. Yeah. Okay. So it's 11:10. We'll come back at 11:30. Otherwise, I have no hope of finishing what I planned to finish. Okay.
Closing the session.
This slide.